Hello class, today we are going to continue with the rigid rotor model and derive the eigenvalue for energy. So the eigenvalue was presented last class, shown here, with being equal to h bar squared times m sub l squared divided by 2 times the reduced mass times the square of radius. So what we're going to do today is show exactly where this equation comes from, and in the process introduce a few new ideas. So to begin, we need to go back to chapter 2 with the non-dispersive wave equation. So this takes us back to equation 2.8, which is the traveling wave equation shown here, where we have wave function psi that's dependent on x and t, position and time, is equal to a sine times kx, or a sine of kx minus omega t plus phi, where k is our wave vector, omega is our wave frequency, and phi is our phase angle. So just remember now that this phi is not our rigid rotor phi angle. So this is a different phi that we're gonna get rid of immediately. So this traveling wave equation simplified to a time-dependent wave function. Psi of x and t is equal to 2 times a times sine of kx times cosine of omega t. And then in chapter 4, we showed the time-independent wave function is just psi of x is equal to a times sine of kx, where k is equal to n times pi over a. And this is really important because n is our principal quantum number, and this is important for the particle in a box model for a ground state versus excited state energy levels. And so when we make the substitution, we get our wave function psi of x is equal to a times sine of n pi x over a. Now, the new idea that we're going to introduce today deals with imaginary components. So while classical waves, like sound waves, only have real amplitudes, quantum mechanical wave functions can also have complex amplitudes with imaginary components. So first, to introduce this idea, let's take a look at sine of x. So you can put any of these equations into Wolfram alpha and get these graphs out. So if you just graphed sine of x, it would look something like this, right? Where we have an intersection at the origin, and we have nodes at intervals of integer values of pi. So negative pi, negative 2 pi, negative pi, 0 pi, 1 pi, 2 pi, etc. And so when we graph the sum of cosine x plus I sine x, we get two wave functions that are slightly offset from one another, where in blue we have the real part of cosine x, and in red we have the imaginary part, sine x. And then over here we can see that if we offset the value of x by pi over 2, and we take the cosine of that quantity and add that to I sine x, we actually see that these wave functions overlap perfectly and become the same. So we'll get back to this here in 1 second. So far, we've only considered the real part. So again, psi of x is equal to sine of kx, and when normalized, it's equal to a times sine of kx. When considering the complex form, the full wave function equation is as follows. Psi of x is actually equal to cosine kx plus I sine kx. And when normalized, it's equal to b cosine kx plus I a k sine kx. Now, this form of the wave function is expressed in trigonometric functions, so things like cosine and sine. But it can also be expressed more concisely in the exponential form using the Euler relation. And the Euler relation is as follows. E raised to the I times alpha, where alpha is any variable, is equal to cosine of alpha plus I sine of alpha. And that is exactly what we have up here. We have, instead of alpha, we have x. So cosine x plus I sine x is equal to e raised to the ix. So e raised to the ix, when plugged into Wolfram Alpha, will show you a graph that is two wave functions, showing the real component and the imaginary component. And so, when normalized, if we had a e raised to the I alpha, that would be equal to b cosine alpha plus I a sine alpha. And so we can take our wave function and rewrite it in exponential form. So psi of x is equal to cosine kx plus I sine x, which is also equal to e raised to the power of I kx. So it takes the imaginary component and the real component, squashes them together, and really just gives you a more simple equation to deal with. So let's continue discussing the rigid rotor wave function, but this time in the exponential form. So if psi of x is equal to a times e raised to the I kx for a time-independent wave function, k contains the principal quantum number n, as we saw on the last page. Now when we go into the rigid rotor model, we have here our phi, capital Phi, which is our new wave function. So our rigid rotor wave function is equal to a times e raised to the I m sub l times phi. Because for the rigid rotor model, the relevant quantum number is the angular momentum quantum number m sub l. And instead of position, we have an angle. So for this exercise, exercise 12, we are going to determine the normalization constant for the rigid rotor wave function in the exponential form a times e raised to the I m sub l phi. So let's do that. First, what we're going to show is that on an integral from 0 to 2 pi, we have the rigid rotor wave function complex conjugate times the rigid rotor wave function is equal to 1 when you integrate over all of it from 0 to 2 pi. For the particle in a box model, we integrated from 0 to a. For rigid rotor, since we're dealing with a circle, in 2 dimensions, we're going from 0 to 2 pi. And so let's bring in our wave function equation for our wave function and see what we get. Now, the first wave function is the complex conjugate. Now, so far, this hasn't been very relevant to us, but now we have a wave function that contains an imaginary component. And so when we bring that in for the complex conjugate, that I becomes negative. So this is, I think for the first time, we're really using this in an integral. So we have from 0 to 2 pi, we integrate, and it's a times e raised to the negative I m sub l times phi times a times e raised to the I m sub l times phi. And when we integrate from 0 to 2 pi, this has got to be equal to 1, meaning that we have a 100% chance of finding the wave function between 0 to 2 pi in 2 dimensions in a circle. And so a times a is a squared, and we can bring that out in front of the integral, and what we have left with is the complex conjugate times the wave function itself is equal to 1. And so over here, we can simplify that. So e raised to the negative I m sub l phi times e raised to the positive I m sub l phi is equal to e raised to the sum of those two exponents. And when you add those exponents together, you get e raised to the 0, which is just 1. So now we can plug in 1 for the product of our wave function and its complex conjugate. And what we're left with is a really simple integral where we have a squared times the integral from 0 to 2 pi of 1 is equal to 1. And so when we integrate from 0 to 2 pi 1, we get phi, with respect to phi, we get phi and we evaluate from 2 pi to 0. And so this integral is equal to 2 pi minus 0, which is equal to 2 pi. And so we can plug in 2 pi for our integral, and we get a squared times 2 pi is equal to 1, which means that a squared is equal to 1 over 2 pi, and a, our normalization constant, is equal to the square root of 1 over 2 pi. Really, not that bad. The exponential form is a little weird, but with this complex conjugate, it simplifies the integral greatly. So we have a rigid rotor wave function is equal to a, our normalization constant, times e raised to the power of I m sub l times phi, which is just equal to the square root of 1 over 2 pi e raised to I m sub l phi. Now, I would argue that this is much more straightforward than normalizing the trigonometric wave functions, which is shown here. So now that we have our normalization constant, we can derive our eigenvalue for the rigid rotor model, and we're going to do this twice, the first time in the exponential form. So shown here is our Hamiltonian times the wave function for the rigid rotor, capital phi, where capital phi is equal to the square root of 1 over 2 pi times e raised to the I m sub l times phi. So this whole normalized wave function gets substituted in for our rigid rotor wave function here, and what we're left with is negative h bar squared over 2 mu r naught squared times the second derivative of our rigid rotor wave function normalized. So 1 over 2 pi, the square root of 1 over 2 pi is a constant, so that can come out in front of the second derivative. And what we need to do now is evaluate the second derivative of e raised to the I m sub l phi. And so that derivative is drawn over here, unfortunately really small, but the first derivative of e raised to the I m sub l phi is equal to I times m sub l times the wave function. And then when we take the second derivative, we find that it is equal to I squared times m sub l squared times the wave function. And if the square root of negative 1 is equal to I, then I squared is equal to negative 1. So the second derivative of e raised to the I m sub l phi is really equal to negative 1 times m sub l squared times e raised to the I m sub l phi. And so we can take this whole thing and plug it in for our wave function. So the second derivative of our wave function is now calculated, and so our expression then simplifies to negative h bar squared over 2 mu r naught squared times the square root of 1 over 2 pi times I squared times m sub l squared times e raised to the I m sub l phi. Now I squared is equal to negative 1, and so when we plug that in, we get this expression here, and the negative 1 from our second derivative cancels with the negative 1 in front of our h bar squared, and that gives us our final expression, which is h bar squared times m sub l squared, which comes out in front as a constant, divided by 2 mu r naught squared times 1 over 2 pi, or the square root of 1 over 2 pi times e raised to the I m sub l phi. Now, here we have this whole clump of constants is now equal to our eigenvalue for energy. And what we have here is our wave function brought back. And so now we have our derived eigenvalue. So our eigenvalue E sub ml is equal to h bar squared times m sub l squared over 2 mu r naught, and our wave function comes back normalized as root 1 over 2 pi times e raised to the I m sub l phi. Now we can also derive our eigenvalue with our normalized rigid rotor wave function using trigonometric identities. And we'll do that here. So here we have our Hamiltonian times our operating on our wave function rather. And our wave function this time is normalized to be equal to the square root of 1 over 2 pi times cosine m sub l phi plus I sine m sub l phi. And so when we substitute that expression for our wave function, what we're left with is negative h bar squared divided by 2 mu r naught squared times the square root of 1 over 2 pi times the second derivative of our wave function. And so the second derivative of the wave function is calculated over here out to the right, where the first derivative is equal to m sub l times negative sine m sub l phi plus I cosine m sub l phi. And the second derivative is equal to m sub l squared times negative cosine m sub l phi minus I sine m sub l phi. And so if you just follow the derivatives, the derivative of cosine is negative sine, and the derivative of sine is cosine and the negative stays the same, and the derivative of sine is cosine and the derivative of cosine is negative sine. So that's how that all happens. And we can now plug in our value for second derivative into our equation, and what we're left with is the simplified version where we have negative h bar squared over 2 mu r naught squared times the square root of 1 over 2 pi times m sub l squared times the quantity negative cosine m sub l phi minus I sine m sub l phi. Now we can factor out a negative 1 from our trigonometric quantity here. And when we do that, we're left with, in parentheses, positive cosine m sub l phi plus I sine m sub l phi. And here is the negative 1 that we factored out. The negative 1 then cancels with the negative in front of h bar, and we're actually left with our final answer, where we have our eigenvalue is h bar squared times m sub l squared divided by 2 mu r naught squared times our wave function, which is still normalized as root 1 over 2 pi times the quantity cosine m sub l phi plus I sine m sub l phi. And finally, to rewrite this, we are left with our eigenvalue is equal to h bar squared times m sub l squared divided by 2 mu r naught squared, and our wave function, still normalized, is equal to root 1 over 2 pi times the quantity cosine m sub l phi plus I m sub l phi. And so again, this expression here just comes from the Euler relation, and the eigenvalue is our expression for energy, which we presented last class.